Hey Chem Fam, we are back and starting to learn about specific heat capacity. We are using our new equation Q equals mc delta T. Don't forget, quick reminder, delta T stands for the final minus the initial temperature. That's super important. Always do final minus initial. Otherwise, you might end up with a negative when you don't need one or a positive when you don't need one. So just be minded of that and you should be good. All right, if we look at number one, it says how much energy is needed. So first of all, how much energy is needed? That's going to be my Q value. Q stands for heat or energy. How much is needed to heat 30 grams of water? So right away, I already know I have a mass of 30 grams. And the water temperature is going to go from 22 degrees to 37 degrees Celsius. So my starting temperature, it looks like it's at 22 degrees Celsius, and my final temperature is going to be at 37 degrees Celsius. All right, so it looks like I'm using my equation Q equals mc delta T, which is TF minus TI. But if you notice, we're missing one variable to plug in, and that's our C. C stands for the specific heat capacity, which comes into play right here on this chart right here. Since we're dealing with water, and the water is between 0 and 100 degrees, this must be liquid water. So therefore, on the chart, liquid water's C value, or specific heat, is 4.184 joules per gram degree Celsius. All right, now that we have all that information, I think we are ready to rock. So let's start plugging in. I don't know my Q value, so I'm going to leave that as Q. My mass is 30, and notice that that's in grams, and so is the unit for specific heat, so that's good. My C value is 4.184, and I looked at that off of my chart. And then my final temperature is going to be 37 degrees Celsius. Notice that this is in Celsius too, and Celsius, so that's good. Those eventually will cancel out. And I'm going to subtract my initial temperature of 22. All right, now throwing that in the calculator, if I do 37 minus 22, I end up getting a 15 here. And then if I would just want to rock all of those out so that I can multiply them together, 15 times 4.184 times 30, multiply all three of them together, I end up getting my energy equal to 1,882.8. Now the question is, what units should this be in? Well, for energy, we know that energy is usually either in calories or joules. Since my specific heat capacity had joules in it, this answer is going to be in joules. You can find specific heat capacities that are in calories per gram degree Celsius, and then if that were the case, your answer would have been in calories. But in this case, you ended up with 1,882.8 joules for your first one. All right? So remember, heat and energy can be used interchangeably. They both stand for the letter Q. All right, looking at number 2, it says, what mass of copper? So right away, I know I'm going to be looking for mass. And I know I'm going to be dealing with copper, so just off to the side, I'm going to remember that copper is on my chart if I need that. But I'm going to move on. It can be heated from 20 to 40 degrees Celsius. So if this thing had a starting temperature of 20 degrees Celsius, and now it has a final temperature of 40 degrees Celsius, we can write that down. And it's heated and done all within 100 joules. Now 100 joules, J, joules, is the unit for heat or energy, which is our Q variable. That's important to know your vocab so that you would know, oh, 100 joules, that must be my Q. Now that I have that, I want to know what my mass is, but that means I'm going to have to use the equation Q equals mc delta T, which is final temperature minus initial temperature. I'm still missing my C value, so I'm going to need to look for that. And lo and behold, just what I was thinking about earlier, my specific heat value for copper is 0.385, and that's in units of joules per gram degree Celsius. Now the last problem we did was up here, 4.184, Ask yourself, which one is harder to heat up then, according to their specific heat capacity number? Is it water or copper? Well, since copper has such a lower value, that means it's easier for copper to not only heat up in energy, but also lose energy and cool off and decrease. Again, which is why we use copper in a lot of different cooking, because copper pots easily heat up and cool down so you don't burn things like your sauces and that. Things that are very delicate to cook, copper pots are usually the choice. All right, let's go back though here. We've got our equation. Let's start plugging in. For Q, my heat and energy, I have 100 joules. For mass, I have no idea. I'm going to leave that as my variable. For my specific heat, letter C, I know it's 0.385. And for my final temp, which was 40 degrees, and my initial starting temp was 20, I'm going to plug those in. 40 minus 20 is 20 degrees. And now I have those times M equals 100. Now I'm going to multiply these guys together. And if I throw it in my calculator, it's just 20 times 0.385. And that gives me 7.7 times M equals 100. Hopefully you know what to do from here. Get M by itself, so divide by 7.7 to both sides. That will eliminate 7.7, and you end up with mass is equal to 100 divided by 7.7, which ends up being about 12.99 grams. All right, so that means 12.99 grams of copper would be heated to go from 20 to 40 degrees Celsius if only using 100 joules of energy. All right, you would have about 13 grams of copper. All right, think about that in pennies. Copper is the coating on a penny. So 13 grams of that stuff, only 100 joules of energy would raise it 20 degrees Celsius. All right, number 3 is going to be asking for, what is the specific heat of glass? Taking a look here, glass is on that sheet, but that's okay. We don't need the chart to figure out the specific heat of glass because we have other pieces of info. We know that 735 joules of heat was used. So that's my Q value, right? Anything in joules is my heat or energy. And I know I have 25 grams of glass. So my mass of the glass is 25 grams. And that rhymed too. That was great. The glass is going to now go from an initial starting temperature of 40 degrees Celsius to a final temperature of 75 degrees Celsius. Great. With that in mind, I think I have everything I need in order to figure out eventually my specific heat of glass. So I'm looking for the C value. So if we use our equation, Q equals MC delta T. Delta T means change in temp, which is final minus initial temperature. Now I can plug in and chug out that answer so that I get something quantitative. I know my heat is 735 joules. My mass is 25. I have no idea what my specific heat is, but I do know that my final temperature is 75 and my initial temperature is 40, so I'm going to subtract those two. Now that I have that, 75 minus 40 here is going to get me, what is that, 25? No, 35, sorry. So that's 35, almost wrote 32, sorry. 35 times 25 times C gives me 735. I'm going to multiply 25 and 35 together, and I'm going to end up with 875 times C equals 735. I'm going to divide both sides by 875 so that C can be by itself and isolated. Don't forget, C is the specific heat. So 735 divided by 875 gets me about 0.84 for an answer. Now, what does that mean? 0.84, the units for specific heat capacity would be up there at the top of the chart, joules per gram degree Celsius. So let's look at glass's specific heat compared to others. In fact, glass has a higher rating than quite a few of these. Wow. All of them. Okay, so glass is a similar rating to aluminum, meaning all these guys below, they actually cool off and heat up a lot easier than glass. So glass may be more of an insulator than those. Either way, the lower the number of specific heat, the easier it is to heat up or cool off, or the less it holds on to its heat. The higher the number, like water, liquid water, the more it holds on to heat. All right, last example problem for your homework, and then we'll set you free here. If I have 400 joules of energy, remember energy or heat is Q in thermochem. So that's 400 joules of energy. You're heating 40 grams of mercury. 40 grams is a mass. That's why it's important to know your units. Oh, grams, mass, perfect. You have a starting temperature of 15 degrees Celsius. We want to know what the final temperature will be. Wow, okay, good to know. The only other thing we don't know is the specific heat of mercury, and lo and behold, we have it right here. Mercury's specific heat is pretty low. It's 0.14, also a great conductor of energy. We know that that is joules per gram degree Celsius. I just got that from up here at the top of the chart. All right, so I want to solve for final temperature. To do that, let's use our equation. Energy equals mass times specific heat times the change in temperature. So I think we can plug and chug right now to get our answer. I've got 400 for my heat and energy, 40 grams for my mass. For specific heat, I just looked that up off the chart. It's 0.14. Let me put these in parentheses. I like that better. Final temperature is right here. We don't know what that is, but we know we're subtracting 15. All right, perfect. Let's do some algebra to figure this out. I'm going to leave 400 alone, but I'm going to multiply the 40 times the 0.14, and that's going to give me 5.6 TF minus 15. All right, now to do that, we're going to have to distribute that 5.6 to both of them. So if I move my work over here, I still have 400, but now 5.6 times TF gives me 5.6 TF minus 5.6 times 15. 5.6 times 15 is 84. Okay, so now that I have that, I am going to need to get rid of the 84 to get TF more by itself. So I'm going to add 84 to both sides since it's being subtracted over here. 84 goes away, and I'm left with 484 is equal to 5.6 TF. Now that we have that, we can divide both sides. But let me take this right here and move it up here so we have a little bit more room, all right? Excuse me. 484, there's no decimal there. Let's rewrite that. 484 is equal to 5.6 times final temperature. Since it's multiplying, we're going to divide the 5.6 to get rid of it. That's going to be 484 divided by 5.6. Hopefully this will look like a number that seems realistic for temperature, and it is. It's about 86.4 degrees Celsius. So that means that object went from 15 degrees Celsius to 86.4 degrees Celsius when you added energy in. And that's what adding energy in, if it's positive number here, you're adding it in, that's going to be endothermic because you're putting energy in. If it's giving off energy, that's exothermic. But either way, hopefully you get a better understanding now of the Q equals MC delta T, which is a specific heat equation. All right, thanks for listening, ChemFam. I hope you're doing well, and best of luck with the rest of the practice.